see, now I have to go to this window here. Okay, so it works. Good. The slides of my lectures, I will make them available on my web page. Here's the link, but actually it's easiest if you Google my name. Let me also, right in the beginning, give you some suggestions for the literature, for further reading, if you want to know more about the topics of this course. I have some lecture notes about a semester-length course that I've taught on the foundations of quantum mechanics. They're on my webpage, so you can download them there. There are also several books on the subject, and some books that I would that are selected here that I would recommend. It so happens that all of these books are actually rather recent, and all of these books got published by Springer. Actually, I don't get any money from Springer for saying this. Okay, it just so happened. So some books that I recommend are Brikman, Norsen, and Dürr and Lazarovici. The book by Brikman is more a discussion of which interpretation of quantum mechanics is better than the others. Norsen and Dürr and Lazarovici are more in the spirit of explaining the different interpretations from a modern perspective and explaining what their motivation is, what people have in mind there, how they work, and what the advantages and disadvantages are. Here are some topics that I will touch upon in my 4 lectures today and tomorrow. The Copenhagen interpretation, many worlds, Bohmian mechanics, collapse theories, just such as GRW. GRW stands for Ghirardi, Rimini, Weber, the 3 guys who came up with the first collapse theory that actually works. Quantum measurement and the measurement problem, no hidden variables theorems, the Einstein-Podolsky-Rosen argument, Einstein's boxes argument, Bell's theorem and non-locality, and relativistic versions of several of these theories, such as Bohm's theory or GRW, etc. Okay, let me start. Let me start with just introducing some example of physical theory. We will talk a lot about how fundamental physical theories should be formulated. So I will start with some examples of such theories and how they could be formulated. I will formulate these theories in such a way as if they were actually the true theories of the universe. Even if we know they're not the true theory of the universe, I will formulate them as if they apply to the whole universe, to all phenomena, as if they were the final theory, as if they were a theory of everything. So let me start with a particular example. So here's a particular physical theory. It says the following: the universe consists of the following things. First, a 3-dimensional Euclidean space. I will denote it by E3. Then some number n of material points, which we commonly call particles, that move around in this 3-dimensional Euclidean space as time proceeds. E1 means a 1-dimensional Euclidean space, if you wish, the time axis. So at every time t, every particle has a position q sub k of t in this 3-dimensional Euclidean space. And that changes according to some equation of motion. So here's a particular example of an equation of motion. Mass times acceleration is given by some expression. Oh, you may recognize this expression. The first term is just the gravitational force according to Newton. The second term is just the Coulomb force. So this theory is just Newtonian mechanics. And here, so G is the gravitational constant, M is the mass, and E K is the charge of particle K. So we could, so now at this point, the definition of the theory is complete. So there's a particular theory, a hypothetical universe. Now we can, from these basic assumptions, these basic laws of the theory, we could deduce what the consequences would be, how objects in the universe would behave if this theory were correct. We could deduce what observers living in this universe would see. And as you know, it's not correct in all respects. It gives some things correctly, such as motion of the planets, and some things incorrectly because it doesn't cover quantum phenomena. Okay, here's another physical theory, another example. According to this theory, the universe consists of a three-dimensional Euclidean space, n material points called particles moving in this three-dimensional Euclidean space. Qk of t denotes the position of particle k at time t, and that moves according to a particular equation of motion. Here's the equation of motion. It's a first order equation of motion. For first order in time, that means it specifies velocities rather than accelerations. As the equation of motion of Newtonian mechanics, it's an ODE, an ordinary differential equation. You can specify initial conditions, and then you can solve this this equation of motion. It depends, however, on some function s, and this function s is the phase of a wave function. So the wave function is a complex valued function, and I'm not sure, can you see my pointer here, my arrow?
Yes.
Okay, thank you. Good. So here you can see S is the phase of this wave function. Okay, and that is what appears here. And the wave function itself also changes with time according to the Schrödinger equation. So it's the usual kind of wave function that you would have in non-relativistic quantum mechanics. I wrote it down here with a particular potential, the Coulomb potential. Okay, so it's the usual Schrödinger equation with Coulomb potential. So that would be a simple model of what the world could be like. Now, for this, this theory is called Bohmian mechanics because it was first suggested by David Bohm. Psi is the wave function. Of course, you're familiar with the wave functions from all other versions of quantum mechanics. So this is a particular version of quantum mechanics, however, a version that has particle trajectories, which is, well, normally in quantum mechanics, you don't talk about particle trajectories. You say particles don't have trajectories. Now, Bohm had a different proposal. He had the proposal that maybe particles do have trajectories. And I want to talk a bit about this particular proposal. Now, the equation of motion could be rewritten directly in terms of psi. Let me go back one slide. That was the previous slide. So what I did was just on the right-hand side of the equation of motion, I expressed the gradient of the phase directly in terms of the wave function. So that is the common way how you would write down Bohm's equation of motion. You would say, you take the gradient of psi, divide by psi, take the imaginary part. Well, a two-line computation will show you that this is the same as the gradient of the phase of the wave function. Also, well, here, the way I wrote it down, I used the Coulomb potential, but of course, you can do that with any potential. I could just put here an arbitrary potential function. So Bohmian mechanics can also, of course, be defined for arbitrary potentials. Good. Here is another remark on different ways of writing Bohm's equation of motion. And that's partly because in the literature, you will sometimes find Bohm's equation of motion written in different ways, and partly because you need to understand certain properties of the equation of motion, and some of these properties are best understood if you write them in particular ways. So here I have copied again in the first equation what Bohm's equation of motion looks like. Now I rewrite this as current divided by density. Here by density, I just mean psi squared, what is the usual probability density in quantum mechanics according to Born's rule. And the J vector is the probability current, also the quantity usually considered as the probability current. It has an index k because that refers to particle number k. So the probability current is really a vector field in configuration space. Configuration space here would be 3n dimensional. The configuration being the list of the positions of all particles. And the probability current would be a 3n dimensional vector. So it has 3 components for each particle, and the j sub k, that would be the 3 components belonging to particle number k. Okay, so these are expressions that you have probably seen before: gradient of psi times psi complex conjugate and imaginary part of that product. Okay, now, so we will use the fact, okay, or let me say this, the fact that Bohm's velocity is just the current divided by the density. That is kind of fitting well, that maybe fits well with the idea of a probability current transporting the probability in the direction in which the particles move. Okay, actually we will use this fact again mathematically on the next slide. Here's one more remark about Bohm's equation of motion. Bohm proposed his trajectories in 1952, and in his first paper on the subject, he wrote the equation of motion in a somewhat strange way. He took another derivative of equation 1, which means that on the left-hand side, he had the acceleration, second time derivative of the position, and then he got some other expression on the right-hand side. He wanted to have that because he wanted it to look like Newtonian mechanics. And then he demanded that, in addition, equation 1 is satisfied as a constraint condition on the velocities of the particles. Okay, so when you look into the literature, in particular into Bohm's own papers, you may see this strange way of formulating the equation of motion. It's a kind of more complicated way of saying a simple thing. That's why I'm saying it in a more simple way. I wrote it down in the form that you have that you see here in equation 1. There's one more axiom in Bohmian mechanics, and that is the following. First, let me introduce the notation. Q means the configuration, so the list of all positions. And now we assume that at the initial time of the universe, the configuration gets randomly chosen with a probability distribution that is the psi squared distribution. So we assume that some version of Born's rule holds at time 0, that initially the configuration is chosen randomly with psi squared distribution. Of course, that requires that the initial wave function is square integrable. That's what I wrote here. It's an element of the L2 space and has L2 norm equal to 1, so that this psi square distribution is actually normalized. It then follows that actually the configuration is psi square distribution at every time t. More precisely, if at any time t0, the configuration has probability distribution psi t0 squared, then at any other time t, the configuration qt has probability distribution psi t squared. Here's an outline of the proof, why that is so. You may know that a probability density rho gets transported by the motion. So if you have a law of motion on some space, in this case on the configuration space R3n, with a particular velocity field on R3n. So that here I mean the velocity field, the 3n dimensional vector field on configuration space which for particle number k has the components vk, then you get this continuity equation for the transport of rho. Now, on the other hand, so here for this equation, rho is kind of arbitrary. You could choose the initial data with any, say randomly with your favorite probability distribution rho, and then the probability density would be transported according to this equation. On the other hand, the Schrödinger equation implies a continuity equation that looks like this. If you just compute according to the Schrödinger equation what the time derivative of psi squared is, you get an expression that is the negative divergence of all the probability current. Now, it's a relevant fact that these two equations have the same structure. In fact, the J could be written as the V times psi squared, because that is how V was defined. You remember that the Bohmian velocity was the current divided by the density. It's J divided by psi squared. So writing the J as V times psi squared, you see it's the same equation, just with rho replaced by psi squared. Now, as a consequence of that, if at any particular time rho equals psi squared, then it follows that the time derivative of rho equals the time derivative of psi squared. So if rho equals psi squared at any particular time, it stays equal to psi squared also at the next time step and the next and the next. Okay, so from this it follows that actually rho is equal to psi squared at all times. Let's look at what Bohmian mechanics actually looks like, what the trajectories look like. So here's a simple example, the double-slit experiment. In this picture here, I've drawn some Bohmian trajectories. So the idea here is that this thing here on the left is some kind of screen that has two slits. Here's slit number one, here's slit number two. Now the wave function is coming from the left, and where it hits the screen, it's absorbed or reflected, but where it hits the slits, it passes through. So some wave function passes through each of the slits, and behind the slits, they spread like a circular or spherical wave. They will overlap in this region. Waves coming through the upper slit and through the lower slit form an interference pattern. Now in this picture, I've drawn the Bohmian trajectories. In fact, alternative possible trajectories. So in this picture, there are actually 80 trajectories. The idea here is that according to Bohmian mechanics, the particle will just follow one of these trajectories, and which one, that is random. So every time you do the experiment, the wave is coming from the left and moving to the right. Also the particle, the particle, the position of the particle is always psi square distributed. Okay, so the particle will be in the region where the wave function is significantly non-zero. If the wave function is very close to zero, then the particle has very low probability of being there. Okay, so the particle is also coming from the left. It's passing through one of the slits. Since it's a particle, and since it follows one of these trajectories, it actually goes either through the upper slit or through the lower slit, whereas the wave function goes through both slits. So in Bohmian mechanics, you have wave-particle duality in the literal sense. You have a wave, and there is a wave and there is a particle. The wave passes through both slits, the particle always only through one. Which one? That is random. Okay, so the particle follows one of these trajectories, a random one. And what you can see here in the picture, actually, is the distribution of the arrival points. Say at this location here, we put a screen, a photoplate, or something where we can see where the particle arrives. You see that there are some regions where lots of particles arrive. There are other regions where very few particles arrive. Few trajectories, that means the probability of arrival there is small. Okay, if you repeat the experiment over and over, you will have few particles arriving in this region. So what you see here then on this, in this location, if you put there a screen, you will see an interference pattern. Every time you do the experiment with one particle, you get one spot on the screen. If you repeat it many times, you will get a psi-squared distribution of your of these arrival points, and you will see an interference pattern, bright and dark fringes, which is exactly, of course, what you see in our world when you actually do this experiment. You can do this experiment with individual electrons and kind of get one spot in every single run of the experiment. So you see in this, you somehow see in this picture how the interference pattern actually arises. You can see that that Bohmian mechanics leads to the prediction of the correct interference pattern. In a way, it has an explanation of why you would have this interference pattern, because, well, the motion of the particle depends on the wave function. You can see this, of course, in the trajectories. The trajectories are curved. They're not straight lines. They're not the same trajectories as in Newtonian mechanics. In Newtonian mechanics, the particle would also pass through one of the slits and then move along a straight line. Maybe the straight line would not be completely horizontal for some reasons of, I don't know, interaction with this screen. Maybe it would not go exactly horizontally, but it would go along a straight line, and then you wouldn't get any interference pattern. So here the trajectories are very non-Newtonian. That's because you have a different equation of motion. You don't have Newton's equation of motion, you have Bohm's equation of motion, where the motion of the particle depends on the wave. Now let me connect this with what Feynman wrote in his lectures on physics in 1964. Volume 3 is about quantum mechanics, and the first chapter of this volume is about the double-slit experiment. He has a very nice discussion there of the double-slit experiment. He explains what you would expect classically, what if you had classical particles, what if you had classical waves. Okay, with classical particles, you wouldn't see any interference pattern, but you would have individual spots. With classical waves, you wouldn't have any individual spots, although you would have interference. Okay, and then he says, now in quantum mechanics, when we actually do the experiment, we see the individual spots with this distribution, this psi-square distribution that displays interference. Now that's a big mystery. And then he goes on to say, we cannot make the mystery go away by explaining how it works. And later on he says, many ideas have been concocted to try to explain the curve for P12. This means P is the probability distribution on the screen, the psi-squared, and 1, 2 refers to the case where both slits are open. So he works out that if both slits are open, you have interference terms, you have maxima and minima. Feynman went on to say, none of them has succeeded. And no one has found any machinery behind the law. No one can explain any more than we have just explained. What he has just explained is just say what the outcome of the experiment actually is. No one give you any deeper representation of the situation. We have no idea about a more basic mechanism from which these results can be deduced. Now, these statements, you realize now, are actually too strong, because Bohmian mechanics does just that. It gives you a machinery, a mechanism, a picture of what actually happens during the experiment, that actually makes the mystery go away completely. So, I mean, the idea that you have a wave and a particle, there's nothing mysterious about that. The idea that the equation of motion for the particle could depend on the wave, there's nothing mysterious about that. So I'm saying this as a kind of warning that even from excellent people such as Feynman, you can sometimes find inaccurate information about quantum foundations in the literature. Now let me move on to another experiment, kind of extension of the double slit experiment. That's Wheeler's delayed choice experiment. Here's how that works. So again, you have this double slit. You see here this screen with the two slits. Here's a slit. Here's a slit. Okay, here's the source S, and a wave function B is coming from the source. Okay, so part of it passes through the two slits. And then these are two lenses that somehow redirect the direction of propagation of these wave trains, so that they, instead of going apart spherically, they are focused now in one direction. So they form more or less a plane wave. You see that here as B prime. So there's a or with electrons, so lenses, you could do that with photons, or with electrons, you would have to arrange some sort of potential that will focus the wave function to move in this direction to become more or less a plane wave. So then this plane wave here moves in this direction and arrives here at a particle counter, C1. And this wave moves in this direction, passes through this region here. Here, for a moment, these two waves, they overlap, they interfere, and then they separate again, and this wave coming from here then falls on counter C2. But you also have an option. The experimenter might push in a photoplate in this region, or some kind of screen that will detect particles. So the experimenter has two options for this experiment: either push in the plate or not. So without the plate, one of the detectors, one of the counters, C1 or C2, will click. And with the plate, you will get a spot on the plate. And of course, since the plate is in the interference region, what you would see on the plate after many runs of the experiment is an interference pattern, just as usual in the double slit experiment, just like the interference pattern that we just talked about. Okay, now Wheeler reasoned as follows. With the plate P, we see an interference pattern, so the electron must be a wave and must have passed through both slits. Without the plate P, if the lower counter C1 clicks, then the electron must have passed through the upper slit, slit 1, and be a particle. However, if counter 2 clicks, then the electron must have passed through slit 2 and be a particle. And in addition, one of the points here is this choice of whether or not to put in the plate P could actually be made at a very late time, at a time at which the electron has already passed the slits. So it seems as if we could choose later whether the electron earlier went through slit, whether it went through one slit or two slits. Okay, now that sounds very paradoxical. And it seems like even harder to explain for anybody who would suggest particle trajectories. But now we realize that actually Bohmian mechanics has no problem explaining that. You see what happens in Bohmian mechanics. Okay, so the wave function passes through both slits. The particle passes through one of the slits. Then you remember the picture with these curved trajectories. Okay, so the trajectories in the end arrive in this interference region in places that are psi-square distributed. So if you put a plate there, there's no surprise that you get psi-square distributed spots displaying interference fringes, bright and dark fringes. But if you don't, then of course the particles will move on. They will follow the wave packets. You know, the probability distribution of the particle position is always psi squared. Okay, so if psi goes in two places, then the psi squared distribution is concentrated in these two places. So you get a 50-50 probability of the particle arriving in C2 or C1. So here's an actual computation of what these Bohmian trajectories look like. Notice there's no retrocausation involved. Retrocausation means that a cause in the future could have an effect in the past. Now, the way Wheeler described the delayed choice experiment sounded much like retrocausation, as if you could influence what happened at the passage through the slits. Now here you see if you have both a wave and a particle, then no such influence is necessary. And nothing is left of the sense of mystery. You can also see in this picture here, when you consider a cross section, let's say here in this, this place where you put the plate P, there is actually an interference pattern here. You can see that these trajectories there are more trajectories in some regions that look like dark fringes here and fewer in other regions. There's another observation we can make about this picture, about the Bohmian trajectories. Let's see, for this I'd like to make a drawing. Let me use this here for making a drawing. I'm not sure whether this will work well. Okay. So here are some trajectories. The trajectories actually don't intersect. The fact that they don't intersect has the consequence that actually the trajectories that come from down here don't end up here. They never cross the symmetry axis, which is over here, but they go down again. Okay, so actually if you can see this in the picture, if you in the simulation, if you look hard, actually the trajectories in the upper half, they stay in the upper half, and those in the lower half, they stay in the lower half. That's curious. Why is that curious? Because it's the opposite of what Wheeler thought would happen. Wheeler thought that if the electron passes through the upper slit, then it arrives at the lower counter. And if it passes through the lower slit, then it arrives at the upper counter. Well, that is true if only one slit is open. If only the upper slit is open, then all of the wave function goes here and all of the trajectories then look different. They don't have these curves, okay? They're straight lines then. But if both slits are open, the trajectories change, and then it's no longer true that the trajectories coming from up here end up down there. Okay. Moreover, other aspects of Wheeler's reasoning now appear strange. For example, this one. If one assumes, as one usually does in orthodox quantum mechanics, that there are no trajectories, and if at the slits there were no detectors, then there is no fact about which slit the electron went through. Because, well, if you believe in trajectories, then of course there's a fact, there must have been a fact which slit the trajectory went through. Or if you put detectors at the slits, then you find out, you detect the electron at one of the slits. But if neither was the case, then there is no fact about which slit the electron went through. Now, Wheeler claims the counter in the end later reveals which slit the electron took. But how can anything reveal which slit the electron took if the electron didn't take a slit? So some steps in Wheeler's reasoning appear illogical once you start thinking about it in Bohmian terms. So now let me repeat this one remark that I made a couple of minutes ago, if the particle actually passes through the upper slit, it will end up in the upper detector, the opposite of what Wheeler took for granted.
Sorry,
sure.
I have a quick question.
Please.
About these trajectories. So do they never cross paths, these trajectories, or is it only in this example?
The answer is that in configuration space, they never cross. The reason why they don't cross in configuration space is that the equation of motion is a first order equation. Now for a first order equation, two solutions cannot cross, because if they had the same position at any particular time, then the equation of motion would specify what the velocity is. So you couldn't, if two trajectories crossed, then you would have an ambiguity of two different velocities at the same location at the same time. So in configuration space R3n, they cannot cross. And then, well, if you have several particles, then possible trajectories of particle number one could cross in 3 dimensions as a consequence of the fact that the 3-dimensional picture is then just a projection of the 3n dimensional situation. Okay, so now in this case, it's just a one particle situation, and therefore then the trajectories cannot cross in 3-dimensional space. So,
okay, makes sense. Thank you.
Good. So here Wheeler's reasoning was that because when you think about what happens to the wave packets if you have just one slit open, he thought he could conclude from that where the electron must have gone through. But this is a non sequitur. It doesn't follow. It's a fallacy, a wrong conclusion. I will call it Wheeler's fallacy. I need a name for it because it's a very tempting wrong conclusion. It's a fallacy that often happens, that everybody is inclined to make when thinking about what happens in terms of the wave packets. Everybody is tempted to jump to certain conclusions about where the trajectory should go. And well, if you have an actual model that has trajectories, you realize that these conclusions are sometimes not correct. Okay, the next topic I want to talk about, I want to briefly review the rules of quantum mechanics and then talk about how that is compatible with the Bohmian trajectories. Okay, so here the rules that I have in mind are the following. There are rules for making empirical predictions, and there are rules that essentially all views about quantum mechanics agree about. So these rules are not controversial, they're universally accepted. First rule, the unitary evolution. The wave function psi of an isolated system evolves according to the Schrödinger equation. Here I've written down the expression, the exponential of the Hamiltonian. H is the Hamiltonian, and the Hamiltonian operator in Hilbert space script H. Second rule, Born's rule. When an observer makes a quantum measurement of the observable script A associated with the self-adjoint operator A, which, let's say, has spectral decomposition given by this formula. Here, alpha are the eigenvalues of A. P alpha is the projection to the eigenspace of operator A with eigenvalue alpha. Here, I'm assuming that the operator A has discrete spectrum. Yeah, so for our purposes here, it's sufficient to focus on observables that are self-adjoint operators with discrete spectrum. Okay, when an observer makes such a quantum measurement on a system with a wave function psi, then the outcome of the measurement is one of the eigenvalues, and the eigenvalue alpha has probability given by this formula. You take the norm squared of the projection of psi to the eigenspace. So that is the size of the part of psi in this eigenspace, or it can be equivalently written in this way. It's equivalent because for a projection, p squared is the same as p. That's because the eigenvalues are 0 or 1. And if you replace p here by p squared, you can pull one factor of p on the other side because it's self-adjoint. You don't get a p star, you just have p then. So then you have the scalar product between p alpha psi and p alpha psi, which is the left-hand side. Okay, third rule, the collapse rule. Suppose somebody has done a quantum measurement of the observable script A, has obtained outcome alpha, then the wave function collapses as follows. Here, t minus means the time just before time t. So we're talking about the left limit of the function. So if we think of psi as a function of t, now we're looking at the left limit at t. So that is the wave function just before the quantum measurement. You take that. So that's the wave function that goes into the quantum measurement. You project it to the eigenspace. You divide it by the norm to normalize it. Okay, that gives you the wave function immediately after the measurement. Good. Now, let me go back to the previous slide. Okay, in Bohmian mechanics, the unitary evolution, since Schrödinger's equation is one of the axioms of Bohmian mechanics, it's not a surprise that you have unitary evolution there. We saw Born's rule for position there, but Born's rule for position is not the same thing as Born's rule for arbitrary observables. Okay, so one question that arises is whether that's also true, whether you would get the same probability for other observables than position. And one thing that seems even more dubious is the collapse of the wave function, because in Bohmian mechanics, we assumed that the Schrödinger equation is an axiom of the theory, and the Schrödinger equation means there's no collapse. It's always unitary. Okay, now you need to pay attention to the following aspects. The wave function of the universe never collapses in Bohmian mechanics. So in Bohmian mechanics, I formulated Bohmian mechanics as a theory of the whole universe. Okay, just like I formulated Newtonian mechanics as a theory of the whole universe. And I talked about the wave function. So that would be the wave function of the universe. So here on my slide, I write it as capital psi. So here's a capital psi, and here's an uppercase psi, and here's a lowercase psi. Okay, so the uppercase psi is the wave function of the universe. It doesn't collapse. But actually, when we talk about wave functions, usually we mean the wave function of a system. Now, in Bohmian mechanics, there's a simple definition of what you would say the wave function of a system is. You would say it's the conditional wave function, which means the following. You take the full wave function, which is a function of, let's say, the configuration of some system and the configuration of the rest of the universe. Okay, now for the rest of the universe, you take the Bohmian configuration. Okay, plug that into the wave function of the universe. You get a function that still depends on lowercase x. So here, always lowercase letters. Well, when we talk about configuration, the lowercase letter is like lowercase x is the variable, the generic configuration. That's because you have a wave function that's a function on configuration space. Okay, whereas the capital X or capital Y is the actual configuration. So in Bohmian mechanics, remember, you have a function on configuration and you have a point in configuration space. Okay, so the point, that's the capital X and capital Y. These are the components of the point. And lowercase x and y are the variables in psi. Now, putting a capital Y here means inserting the actual configuration. This is an operation that you couldn't do in orthodox quantum mechanics, but you can do it in Bohmian mechanics. And then Okay, then you put a normalizing factor here in front. This thing is called the conditional wave function of the subsystem, the X system. Okay, now there are some cases in which the conditional wave function evolves according to the Schrödinger equation again. That is when the full wave function is disentangled, that is, if it factorizes, and if there's no interaction, so it stays factorized, okay, then the conditional wave function is actually the same thing as this first factor, and that will evolve according to some Schrödinger equation for fewer particles. But in general, the conditional wave function does not obey a Schrödinger equation. It obeys some complicated dynamics that depends on the whole complicated thing, the whole capital psi and the whole capital Y. Okay. And as a consequence of that, in a measurement situation, the conditional wave function actually collapses. So this is what I want to explain next. But first, I think we should have a short break